Let us discuss about the lanthanoids and actinoids. Lanthanoids and actinoids. Now first we'll discuss about the lanthanoids, and about lanthanoids, these are the elements from F block of the periodic table, from cerium to lutetium. Cerium atomic number is 58, to lutetium atomic number is 71, in which the filling takes place, in which the filling of electrons takes place in the anti-penultimate. Anti-penultimate means the third last. Anti-penultimate 4f subshell. Now the valential electronic configuration of the lanthanoids is, it's a xenon 4f 0 to 14, 5d 0 to 1, and the 6s 2. Now some books they also include lanthanum along with lanthanoids in the F block. Now lanthanum electronic configuration 57 is the atomic number, is xenon 4f0, 5d1, and the 6s2. So there is no electron in the 4f subshell. Now three more important electronic configurations are, one is the next element called cerium 58, and its electronic configuration is xenon 4f1, 5d1, and the 6s2. And then we write the last element, that is called lutetium. Atomic number is 71, where the F subshell is fully filled, xenon 4f14, 5d1, and 6s2. Then we can write the electronic configuration of the second last element called ytterbium. Atomic number is 70, and electronic configuration is 4f14, 5d0, and the 6s2. And one electron jumps from 5d to 4f to make the 4f fully filled and gives extra stability in the ground state. The next one is europium. Atomic number is 63, where the configuration is xenon 4f7, 5d0, and 6s2. Now again in this case the one electron jumps from 5d to 4f to make the 4f half filled and gives extra stability to the element in the ground state. Now next point is, as we move from cerium to lutetium, there is a regular decrease in size. There is a regular decrease in size as atomic number increases. Now this is known as lanthanoid contraction. This is called lanthanoid contraction. Very important term, lanthanoid contraction. So this regular decrease in size amongst lanthanoids is known as lanthanoid contraction, and the cause or the reason for the lanthanoid contraction is, now this lanthanoid contraction is due to the poor shielding effect of the 4f subshell. So all valence electrons are drawn closer towards the nucleus and size decreases towards the nucleus, and the size decreases. The next, this lanthanoid contraction affects the properties of the following 5d series elements in the D block. Now the consequences of lanthanoid contraction. Consequences of the lanthanoid contraction. Now the first is, due to lanthanoid contraction, zirconium and the hafnium have a comparable size. comparable size, exist together in the earth crust, in their minerals. In fact, all 5D series elements have a size comparable to 4D. Now, second consequence is that all 5D series elements have a higher ionization enthalpy than a 3D or 4D series. And the third is that the basicity and the solubility of hydroxides MOH whole thrice decreases from lanthanum to lutetium. So these are some consequences of lanthanoid contraction. Now next point is that lanthanoids also shows a common oxidation state of +3. This is due to the involvement of two 6s electrons and one 5d electron. Now exceptions are there. One is the cerium. Now cerium shows +4 because cerium +4 has a configuration of xenon 4f0. Now another exception is ytterbium, which shows +2 because ytterbium +2 has a configuration of xenon 4f14. Another exception is europium, which also shows +2, and europium 2+ has a configuration of xenon 4f7, which is half filled. Now as we know, lower oxidation states are reducing agent and higher oxidation states are oxidizing. So cerium +4 is a strong oxidizing agent. It easily gains one electron to form a common oxidation state of +3. It is a strong oxidizing agent, whereas europium 2+ and ytterbium 2+ are strong reducing agents. They can lose one electron to attain the common oxidation state of +3. So they are strong reducing agents. Now next point, lanthanoids also shows color and paramagnetism due to the presence of one or more unpaired electrons. Now this lanthanum 3+, which has a configuration of xenon 4f0, and lutetium 3+, which has a configuration of xenon 4f14. Now both these ions are colorless and diamagnetic due to the absence of any unpaired electron. Now these lanthanoids are used in steel industry in the formation of alloys. Now one important alloy is the mixed metal, and this mixed metal contains 90 to 95% are lanthanoids, 4 to 5% iron, and the rest is calcium, silicon, sulfur, like this. Now all lanthanoids All lanthanoids are non-radioactive except promethium. Except promethium. PM is the symbol. Now next is about the actinoids. So we'll discuss about actinoids. Now actinoids are the elements, this is the first point, are the elements from thorium, atomic number is 90, to lawrencium, symbol is Lr, atomic number is 103, in which the filling of electrons takes place in the anti-penultimate 5F subshell. Again, some books they include actinium also along with actinoids in the F block. Now general configuration is radon 5F 0 to 14, 6D 0 to 1 and 7S 2. Next point is a 5F subshell is more diffuse and has a poor shielding effect than 4F, and 5F subshell protects the valence electrons less efficiently or less effectively than 4F. As a result, 5F, 6D and 7S have comparable energy, and due to comparable energy of 5F, 6D and 7S, actinoids shows variable oxidation states. They show variable oxidation states. And also due to a comparable energy of 5F, 6D and the 7S subshells, due to comparable energy of 5F, 6D and 7S subshells and the radioactive nature of the actinoids, the chemistry of actinoids is much more complicated than the lanthanoids, and also due to ineffective shielding of 5F subshell, the actinoid contraction means the decrease in size amongst the actinoids. Actinoid contraction is much stronger than the lanthanoid contraction. So these are some important characteristics of the lanthanoids and actinoids.